everyone. Today we will learn SYLOW'S third theorem. Before we prove SYLOW'S third theorem, we prove a lemma which says that let P be a SYLOW P subgroup of G, then the number of SYLOW P subgroups of G is equal to order of group divides order of normalizer of P. Now we prove the lemma. We know that order of class of P is equal to order of group divides by order of normalizer of P. Since class of P is equal to Q, where Q is less than equal to group, Q is equal to G, P, G inverse, where G belongs to group, which is equal to set of all SYLOW P subgroup of G. The number of SYLOW P subgroups of G is equal to order of group divided by order of normalizer of P. Now we learn the statement of SYLOW'S third theorem, which says that the number of SYLOW P subgroups of G is of the form 1 plus Kp, where 1 plus Kp divides order group, K being a non-negative integer. Now we will prove SYLOW'S third theorem. Let P be a SYLOW P subgroup of G. Let order of P is equal to P power n. Now G is equal to union X P X P, which is equal to union X belongs to normalizer of P, P X P, union X does not belong to normalizer of P, P X P. X belongs to normalizer of P, which implies that Px is equal to Xp. This implies that Px is equal to Pxp, which implies Px is equal to Pxp. Therefore, union X belongs to normalizer of P, Pxp is equal to union X belongs to normalizer of P, Px is equal to normalizer of P. As P less than equal to normalizer of P and union of disjoint right cosets equals the set, X does not belong to normalizer of P, which implies Px is not equal to Xp, which implies Xp X inverse is not equal to P, which implies order of P intersection Xp X inverse is equal to P power m. Here m is less than n, as in SYLOW'S second theorem, which implies order of P Xp is equal to P power 2n minus m. Here m is less than n. Therefore, order of group is equal to order of normalizer of P plus summation X does not belong to normalizer of P, order of Pxp, which is equal to order of normalizer of P plus summation X does not belong to normalizer of P, P power 2n minus m. Therefore, order of group is equal to 1 plus summation P 2n minus m divided by order of normalizer of P, which is equal to 1 plus P power n plus 1 T divided by order of normalizer of P. Here T is an integer. Since left hand side is equal to integer, P n plus 1 T upon normalizer of P is equal to R, which is an integer. Here R is an integer. Therefore, P n plus 1 T is equal to R order of normalizer of P. Again, as P less than equal to normalizer of P, order of P divides order of normalizer of P, which implies that P power n divides order of normalizer of P, which implies order of normalizer of P is equal to P and U. P power n plus 1 T is equal to R order of group order of normalizer of P, which implies Pt is equal to R dot U, which implies that P divides RU. If P divides U, then P power n plus 1 divides order of normalizer of P, which divides order of group, which implies that P power n plus 1 divides order group, which is a contradiction. Therefore, P divides R implies that R upon P is an integer, which implies that T by U is an integer K, which is equal to R by P. Therefore, order of group divided by order of normalizer of P is equal to 1 plus P power n plus 1 T divided by order of normalizer of P, which is equal to 1 plus P T by U, which is equal to 1 plus Kp. By above lemma, order of group upon order of normalizer of P is equal to number of SYLOW P subgroups of G. Therefore, the number of SYLOW P subgroups is of the form 1 plus Kp, which is equal to order of group divided by order of normalizer of P, which implies that 1 plus Kp divides order of group. This proves the theorem. It should be noted that if order of group is equal to P power n Q, where LCM of P and Q is equal to 1, then the number of SYLOW P subgroups is 1 plus Kp, where 1 plus Kp divides P power n Q. This implies that 1 plus Kp divides Q as 1 plus Kp P power n is equal to 1. If P is the only SYLOW P subgroups of G, then P is normal in G, and conversely. Now we will prove this. By SYLOW'S third theorem, we know that order of group divides order of normalizer of P, which is equal to 1. This implies that order of group is equal to order of normalizer of P. Since normalizer of P less than equal to G, normalizer of P is equal to G. This implies P is normal in G. Conversely, if SYLOW P subgroup P is normal in G, then normalizer of P is equal to G, which implies that order of normalizer of P is equal to order of group. This implies order of group is equal to order of normalizer of P, which is equal to 1. This implies that the number of SYLOW P subgroups of G is 1. This implies that P is the only SYLOW P subgroups of G. Thank you and have a nice day.